Okay, so we will continue with our discussion with file system implementation. So when we would like to implement a file system, we have to define several on-disk data structures to keep track of the files. And we want to keep track of the files also when the power is turned off. So therefore, these are on-disk structures so that you don't lose the information when the power is off, okay? So to keep track of the files. So what are those major structures? Boot control block, which is keeping boot information in that partition, how to boot the operating system from that partition. Volume control block keeps information about the file system sitting in that partition plus information about that partition, like for example, how many blocks are there in that partition. And what is the directory? Where the directory is sitting on that partition is maintained in that volume control block, okay? Plus we should have directory information sitting somewhere on the partition into which we have installed a file system. And we have to have file control blocks, one block per file. So every file will have a file control block associated with it. This will keep information about the file, okay, that's created. For example, the attributes of the file, the location of the data of the file on the disk, and so on, okay. So like the process control block, which is used to keep information about the process, we have file control block that is keeping information about the file that's created, okay. So these are the major structures that we use to implement a file system, and these are on-disk structures, okay? Of course, you can bring some of those structures into memory when a file is opened and when a file is being accessed, okay? So the relationship of those structures like that, a directory structure will have entries, one entry per file, and in that entry we will have the file name and some other information about the file, okay? So when you want to open a file, you first search the directory structure and find the corresponding directory entry where you have some more information from where, using which you can obtain some more information about the file. So the directory entry basically contains a pointer or an address, disk address, for the file control block about that file, okay? So from the directory entry, you can reach to the file control block of the file. In that file control block, you have some more information about the file, okay? Like the file permissions, the dates associated with the file, like creation time, access time, write time, and so on, the owners, and so on, the size of the file, and also you will have information about the data blocks of the file, okay? The blocks, these blocks that contain the content of the file, data of the file, okay? Information about how we can reach to them can be also part of the file control block, like for example the addresses and so on, okay? So initially in the system, if there is no file opened, okay, we have all this information sitting on the disk, okay? The directory information, the file control blocks of the files and so on, and the file content, they are all on the disk, okay? When you open some files, now we can have some of this information brought into memory, okay? Like for example the file control block, which is keeping the attributes of the file and some information about the file, okay? Maybe cached in memory, maybe brought into memory when you open the file, okay? And also the directory entry, okay, corresponding to open file, may be cached into memory as well. So when you open a file, for example, some information may be cached into the file, and we will talk about that now. So normally the files, file data, and directory structure, file control block, and so on, they are all in disk, okay? And they will be always on the disk. But when you open a file, for example, while opening the file, the system, operating system, basically first searches the directory structure to find out the corresponding entry, right? So that assume this is the entry, directory entry corresponding to that file. So now you can fetch it into memory, bring it into memory as well, cache it, okay, in a table like, for example, directory structure table and so on, okay, in the directory table. So that, for example, next time the same process or another process that would like to open the file, that process can first check, or the kernel can first check this table. If the file has already an entry in that table, that means you don't have to go and search the directory structure again to find out the corresponding directory entry, okay. Here you have the information already, okay. So you can cache basically the directory entries for the directories that are accessed currently or in recent time, okay? So plus when you open the file also you can fetch, the system, the kernel can fetch also the associated file control block from the disk and cache it in memory. So it can, for example, insert that file control block regarding the opened file into a table called system-wide open file table, okay? When you open the file, you find out the corresponding file control block. You find that by the help of the directory entry. It will have a pointer or address of the file control block. You get it from the disk and maybe just store it, cache it in the system-wide open file table, okay? You don't delete, of course, it, okay? You are just caching it, okay? You just copy it into memory. So we have still the corresponding file control block on the disk. So we cache it because subsequent operations on the file, many reads, many writes, and so on, will require information about the file. For each such operation, we don't have to go to the file, to the disk, and obtain the information from the disk, okay? You can easily go to the table here in memory and access the related information about the file from the table. And in this way, you can save disk accesses, okay? Access to disk is very costly compared to access to the memory. Plus, you also have per process open file table. So this table is only one table in kernel, okay? So it's a system-wide table. You don't duplicate it for every process, but for every process, regarding the open file, you have to maintain information that is process-specific, like, for example, the current file position pointer, from where the next operation will take place, okay? Initially, when you open the file, it is initialized to 0. It points to the beginning of the file, but when you read, it's advanced, okay? Next read operation will advance it and so on. So file position pointer is advanced for each process. When a process reads, its corresponding file position pointer is advanced by the kernel. So basically, that file position pointer has to be kept as an information that is per process. So it is kept in per process open file table, okay? So basically, we create an entry in that table for the opened file, okay? So when you open the file, basically, a return value from the kernel is given to you, right? You store it in an integer descriptor or in a file pointer variable, okay? So if you open the file using the open system call, the return value is an integer. Basically, it's an index into that table, okay? So that index is returned to the application, okay? You assign it to a variable, and then, for example, ft, integer ft in your application, and then you use that variable or file descriptor, an integer descriptor, in subsequent operations on the file, read, write, and so on, okay? You don't use all the time the file name. So then next time you invoke an operation like read, you use that index, which is the result of opening the file, okay, as argument to read, and now the kernel will understand from that index which entry here corresponds to the file that is to be going to read, and from there it can reach to the corresponding FCB cached in the open file table and so on, okay? And then from here it can obtain information about which data, which disk blocks contain the file data, and it can access those disk blocks to perform the operation, reading or writing, okay? So basically, as a result, we have some disk structures of the file system, and when the files are accessed on that file system, we create some memory structures, objects, and use them, okay? Like, for example, a corresponding object in memory for the file control block, or a corresponding object here for the directory entry, and so on, okay? Any questions here? So usually what we have is, in a computer, like a Linux computer, for example, while using it, you need to access several file systems. You may have a partition 1, in your disk, which is using, for example, Linux, okay? And so there you have extended file system 3, X3 file system. Then you may have another partition on disk that is actually installed Windows, so you have NTFS file system there. Then you can insert CD-ROM. You can access, for example, CD-ROM files. The file system there is, for example, a CD-ROM file system, okay? It is not the file system that Linux is using for the disk. And you can insert a USB flash disk, okay? There you have also a different type of file system. You can have your computer part of a local area network and a part of a distributed file system, so that you can access, you can mount a remote file system to a mount point in your directory tree, and you can access the files there. You can change to that mount point, to that subdirectory in your directory tree, and see the files sitting there and access the files there and so on. That means you are accessing a file system that is remote, okay? And the type of that file system does not have to be the same with the type system that you are using locally, okay? It can be, for example, another total different file system. That means at a given time, you may need to access several files sitting on different types of file systems, okay? So that means your system actually should support all these different file systems. And what is an efficient way of supporting different types of file systems inside a single operating system like Linux? So the answer is virtual file system, okay? So what is done is that besides the concrete file systems that we may need to access, for example, you can have a Linux file system here to access Linux files, you can have an NTFS file system to access NTFS files, and you can have, for example, another network file system to access a remote file system, okay? So we have different types of file systems that needs to be used, okay, to access files sitting in different media, in different locations, and so on, all right? So a single process, for example, may need to access files here, there, and so on, okay? So a single process may use several different types of file systems. So the implementation of those different types of file systems has to be there in the operating system, okay? So what can be done? It is not very convenient, for example, if those file systems has specific interfaces, it is not very convenient to know by a process or by a user to know the specific interface of each of these file systems, okay? Then you have to aware, for example, when you want to access a file, you have to be aware on which file system it is using and what is the operations that that file system is supporting or giving to you to operate on the file. You have to know them. You have to look and learn them and then access the file sitting in that file system. If you now would like to access a different file sitting in another file system, then you have to know the interface of that file system, okay? So this type of solution is not very convenient because then you have to learn various interfaces. What is good is that to have a single interface, a set of operations that you can use to operate files on files that may be sitting on different file systems, okay? So this is what virtual file system is providing, okay? So we have the VFS layer inside the file system, inside the operating system, that is now providing some interface functions to the processors. So the process can call those functions. These are basically the system calls and their implementation. So we have read, write, close, open system calls, right, for the files. And those system calls implemented in the virtual file system, okay, the process can call them. And they can call them, the process can call these same set of operations on all files, no matter whether the file is sitting here, there, and so on. But finally, when you call, for example, an open or read system call on the virtual file system, if that file is sitting here, finally the virtual file system has to call the read or open operation that is implemented here, or a corresponding operation. It may not have the equal name, okay? Finally, the corresponding operation implemented here has to be called because this will be doing the actual job of going to the retrieving the file content and so on, okay? Or opening the file and so on. But the virtual file system can direct the request to concrete file systems when, for example, an application process opens a file and would like to operate on the file, okay? So now, if you would like to integrate a new file system, assume now you have a different media for which you would like to write a new file system, okay? And you want that file system to be integrated into this system, assume this is a Linux system, okay? Into this operating system. What you should do is this. The VFS file system has a well-defined interface here that can be used by applications and also has a well-defined interface here, the VFS interface. A well-defined interface to do underneath concrete file systems. So that if you would like to integrate a new file system here, you write your file system, but also on top of that, you write some functions that are requested by the VFS. VFS layer tells that I want these functions to be implemented by you because I will call those functions while operating on the files, okay? And if you implement those functions to me with this semantic, then you are guaranteed that you will be able to run in this system, okay, and interface with the rest of the system, okay? So then as an implementer of this file system, okay, you will implement the specific concrete file system functions and you will know how to organize your files into that new storage media and so on. But plus you will implement the requested functions by the VFS layer, okay? This can be an open, this can be a read or write function and so on, okay? So then the VFS layer will just call those functions when it would like to operate on files controlled by your file system. Okay? In this way, with the VFS layer, we have an easy integration of new file systems into the system, okay, into the operating system. So any file system that has to be supported by this operating system has to be written or has to have some functions that are written according to the VFS layer so that the VFS layer can call them. Okay? When the VFS layer can call them, that means now the VFS layer can access the function, the files controlled by this new file system. In this way, the other higher layers, the processors, can also call the VFS functions, the VFS interface functions, which in turn can call the functions of the specific file system that you have implemented. And in this way, your file system is also supported in that system. Then you will not get such errors like unsupported file system and so on when you insert a media. Okay? So UNIX is very good in doing that. It can support many different file systems simultaneously, maybe 30, 40 file systems, okay, by such a implementation, okay, by such a layering of the file system. So you have the virtual file system layer, and then underneath you have the concrete file systems. Is the idea clear? So now let's look to other different implementation issues. How can we implement the directories? Let's look to that. Before, for example, how we can implement the files. How can we store and organize the files on the disk? We will look to that soon. But before that, let's look to this question. How can we implement the directories? So what is the job of a directory? The job of a directory is translate a given file name to the corresponding FCB or file data, okay, or file. Basically, when we want to open a file, we have to search the directory. The directory may be a tree-structured directory, okay, containing, for example, 10,000 entries. We have to search that to find the corresponding entry to the file, which will give further information about the file, okay? So we can organize a subdirectory that is part of a directory tree, something like that, as a linear list of entries. Each entry will include a file name plus the address of the corresponding FCB maybe, okay, file control block, so that we can get further information. So if you know that address, then you can go to the disk and retrieve the FCB and get more information about the file, okay? So each directory entry may be structured like that. So then we can have a subdirectory, a sequence of entries. A subdirectory is a sequence of entries where an entry may have an information about a file or it may have an information about another subdirectory, okay? As a result, we have a directory tree, right? A tree-structured directory. So if you look to a subdirectory inside a tree-structured directory, then we have it as a linear, we can have it as a linear list of entries, file names with pointers to data blocks or FCBs. So this is one way of implementing a directory, a subdirectory, okay? Just have it as a sequence of entries, okay? But this is simple to program, but it is time consuming to access. Why? You have to search all these entries whenever you want to search for a file, for a file, okay? And if we have just a few entries, it is not a problem. But if we have, for example, 500 files here, this is a structure sitting on the disk, okay? So you are searching the disk for a matching file, okay? The directory structure is sitting on the disk and you are searching linearly all these entries on the disk for the matching entry given the file name, okay? So this will be time consuming. How can you improve that? We can use a hash table, okay? So given a file name, you can hash it into a table so that you go to a table entry. There you can have, for example, the address of the directory entry, and then you can jump to that entry directly and get information about the file, okay? You can retrieve the directory entry directly if you use a hash table. So these are some implementation issues about the directories. We will not talk much about the directories. Let's look now to this issue, very important issue, one of the primary issues that the file systems handle. How can we allocate disk space to files? Or how can we organize the files on the disk? Okay? Allocation methods. So basically, as we said earlier, a disk is seen by a file system as a sequence of blocks. Then the question becomes this: how can we allocate those blocks, disk blocks, to files? Okay? Initially, it may be enough to allocate just one block to a file. But when the file grows, you need to allocate some other blocks. The question is which block you will allocate. A contiguous block, next block. If there is no, the next block is full, then what can you do, and so on, okay? So these are the issues. So basically we will talk about the allocation methods. An allocation method is how disk blocks are allocated to files. So we will see three basic allocation methods: contiguous allocation, linked allocation, and index allocation. Let's look to the contiguous allocation first, okay? So the idea is very simple here. Like the contiguous memory allocation for processes, you are allocating the disk space contiguously to a files. So if a file is given, now this is the file for which you would like to allocate a space, then you use a contiguous disk blocks to allocate the space, okay? So for example, this file can be located here on this disk. So these disk blocks can be allocated to that file. Then in the FCB, file control block of the file, or in the directory entry, you can keep this information to reach to the blocks allocated to the file. What is that information? The start address, the start block number, where the file is located on the disk, plus number of blocks allocated to the file. For this particular case, how many blocks are allocated? 4 disk blocks. Assume this is the disk, or this is the view of the file system of the disk. So disk is a sequence of disk blocks, numbered 0, 1, and so on. So these are disk block addresses or numbers. So these 4 blocks are allocated to the file. So the start address is 6, okay? Starting at address 6, this block 6, 4 blocks are allocated. If I know that information, which I can keep in a directory entry or in the FCB of the file, then I can obtain all the disk blocks that are allocated to the file, right? I can immediately compute their disk block numbers. And if I am doing a sequential read operation on the file, that means I have to go and access those files, those blocks, block 6, block 7, block 8, block 9, and give the content of those blocks to the application, right? For a sequential read operation. Basically, the file system will compute those blocks. So this file is sitting on disk block 6, 7, 8, 9. And from the driver, it will request those blocks. Please give me block 6, then block 7. So it will issue requests to the read request to the driver. Retrieve block 6, then another read request. Retrieve block 7, retrieve block 8, retrieve block 9, and so on, okay? Then the disk driver is responsible to retrieve those blocks and give the content to the file system, which will give the content finally to the application. The file system may cache those blocks. Of course, before issuing a request to the disk, to the driver, sorry, the file system first, the lowest layer of the file system, first checks whether actually the block is already in the cache. If it's already in the cache, then you don't issue a request to the driver and to the disk. You just satisfy the request from the cache, okay? So this is how we organize a file, the files on the disk now. Contiguous allocation. You allocate a contiguous disk space to a file, a contiguous number of blocks, set of blocks to a file, okay? What is the now disadvantage of that? So files, it may be difficult for a file to grow. If that block is empty, then file can grow. But if that block is used by another file, then the file cannot grow. What is the good thing about that? The good thing about this organization is this. You can immediately compute, for example, the block numbers allocated to the file, right? So if I give you that and that, you can say that, okay, block 6, 7, 8, and 9 are allocated, okay? Plus, you can immediately do this. Assume I would like to access the beginning of the file. You know that it is in that block, right? So immediately you can compute the corresponding disk block number. Assume then I would like to a random jump, and I would like to access that position of the file. I can immediately compute which disk block contains that byte of the file. For example, can you say around which disk block we have that byte? It's probably disk block 9, right? For example, for this byte, we have to access disk block 8 and so on, right? So random access is very efficient. You can access any position in the file and compute the corresponding physical location very fast and go directly there and access it, okay? Random access is very efficient. However, growing the file is a problem. Another problem is the external fragmentation. You can allocate that space to a file, another space, and then sooner or later you will have the disk fragmented. You will have some holes, some set of blocks that are contiguous but cannot hold any file. They are not large enough and so on, okay? So let's look an example for this allocation scheme. Assume we have a file X and file Y that needs to be allocated space. So you can store file X here and you can store file Y here. So then you can keep that information in the corresponding directory entries for these files or in the corresponding FCBs. For file X, you have to maintain this information. It starts at block 6 and occupies 4 blocks. And for file Y, it starts at this block 2 and occupies 3 blocks and so on. Okay? So this information is enough to retrieve all the blocks of the file. Okay? So then we can do such computations. So when we, for example, allocate those blocks to a file and store the content of the file or data of the file in those blocks, that means that file is now mapped here. So here we have, for example, for this file, the bytes of those files can be considered addressed using logical addresses. So this is the byte 0, byte 1, and so on. Okay. So these are the logical addresses into the file. You may want to access any byte at any logical address, right? So basically these are called logical addresses or offsets. So the question is, given an offset, what is the corresponding disk location? For example, offset 0 is located where? On disk 6, disk block 6, right? So for example, offset 2500 corresponds to that disk location and so on, okay? So if you want to access that byte of the file, that means you have to go and access this disk block, right? So let's do an example. The question is, which disk block contains the byte at offset or logical address 2500? In other words, where is logical address 2500 mapped in the disk, okay? So the question is, if you have the picture, the question is very easy to answer. But if you don't have the picture, what do you need to do? So first, we can divide that number, the offset, to the block size. Assume the block size is 1024 bytes. Each block can hold that many bytes, okay? So if this is the offset, in order to find out in which relative block it is, you can divide that with the block size and you can, for example, obtain 2. What is 2? 2 is the relative block number, okay, where that byte is sitting. So that means the relative blocks allocated to file are numbered like that. This is block 0, block 1, and block 2. So 2 is the relative block number of the block allocated to file. What is the disk block number now? 8, right? So you can easily compute that by, for example, adding 2 to the start address, 6. 2 plus 6 makes 8, so 8 is the disk block address, okay? Or disk block number that is holding that byte of the file, okay? Of course, we should also compute the displacement. Inside that block, what is the displacement of the byte that we want to access? Basically this value here. So how can you compute that? You can divide, or you can take the mode, perform the mode operation, okay? 2500 mod 1024 will give you the displacement inside that block, offset inside that block of the byte that is requested, okay? So then we can say that, okay, this logical address, the physical correspondence of that is this block 8 and displacement 452, okay? So this is the logical to physical translation, okay, conversion. So you are given a logical address offset into the file, and then you find out the corresponding disk block number plus displacement inside that disk block, okay? So this gives you the algorithm here. So this was an example. Here you are given a logical address, okay, into a file. You are given a logical address into a file. That's a file offset. It can be 0 or at most file size minus 1, right? You would like to find out the corresponding disk block number and displacement in that disk block. So for that you do what? You divide the logical address or offset, file offset to disk block size. You obtain a quotient and remainder. The quotient is the integer division result, and the remainder is the mod operation, right? Logical address mod disk block size. So now the disk block to be accessed is what? It is the Q plus the starting address, start disk block number, where the file is located on disk, okay? And then displacement into the disk block is what? It is R, okay? You have to go and access that byte inside that block. If you want, for example, to access a byte at that offset in the file. Is it clear? Any questions here? Now let's look another figure that is showing the idea of contiguous allocation. So we have a disk here that has blocks numbered starting from 0, okay, up to 31. So we have 32 blocks here, disk blocks. So assume we have several files in the directory or in the corresponding FCBs. We can keep this information for each file. So for file count, we have the information this. That means the file starts at block 0 and the length, the number of blocks allocated to file is 2. For example, for the file mail, the start block is 19 and the number of blocks allocated to file is 6, okay? So for example, if you want to access the mail sequentially, you have to jump to block 19 and you have to access the 6 blocks starting there, okay? 19, 20, 21 and so on to retrieve the content of the file, okay? So the file mail is sitting here on the disk. File tr is sitting, for example, where? Is sitting here on the disk, okay? It starts at disk block 14 and occupies 3 disk blocks. Is it clear? So, as we have said, the problem with this allocation scheme is that what happens if you would like to grow the file. Sometimes the space after the file may not be empty. So, what you can do? So, the solution to that is using extent-based file systems, now which are doing this. They are allocating disk blocks to files in extents. What's an extent? An extent is a contiguous blocks of disk, a contiguous blocks of disk, okay? So initially you make a guess for your file. You say that the size of my file will be this. Then you go ahead and find an extent, okay? Allocate space for your file, some contiguous set of blocks, and those blocks are given to the file, okay? But however, when the file tries to grow more, then you allocate another extent and put a pointer to point there, okay? This may be a solution. So this was contiguous allocation. Now let's look to another allocation method, which is called linked allocation of blocks to files, okay? Any questions so far? So in this linked allocation, what do we have? Now each file on disk, okay, the data of the file on disk is a linked list of disk blocks. All right? So we have disk blocks that are scattered around on the disk, okay? When we want to grow the file, we just allocate a block, find a free block, and add it to the linked list of blocks for the file. So what we need to do is we just keep a pointer to the beginning of the list, to the first block of the file. So then that will point to the next block of the file, next block of the file, and so on. So each block allocated to a file will have such a structure now. So assume this is a block allocated to a file. It will have data stored somewhere plus a pointer, okay? So in the beginning it may have a pointer, which is an address, disk address or disk block number. So it's a pointer to the next block allocated to the file. Basically it will keep, here we will keep the address of the next block allocated to the file. So initially what we need to do, in the directory entry or FCB corresponding to the file, we can just keep a pointer to the first block. Keep the address of the first block. Using that you can reach to the first block of the file. There you will find the address of the next block. Then you can reach also to the next block. When you go to the next block, you will find the address of the next block and so on, okay? In this way you can access the blocks of the file, okay? So however, in this case what we will have for the data size in the block. So usually the block size is a power of 2. For example, 1024, okay? 1 kilobyte. Or 4096, 4 kilobyte. This may be a block size, okay? So usually block size is a power of 2. But if you use some portion of that block for a pointer, let's say 4 bytes, 8 bytes, okay? Then the remaining portion will be used for data. And the data size in a block now will no longer be a power of 2, okay? So this is something that you should be aware of. So then we have the disk blocks viewed as like that. Each disk block can contain some data, and it will also include a pointer, okay? each disk block is something like that, okay? So this is a disk view. This is how file system is viewing the disk now. A sequence of blocks, block 0, blocks 1, and so on. So now assume you create a file, okay? That will be that big at the end, okay? Initially the file is empty, okay? So assume you start writing into a file. So file is growing now. You have to allocate. If you want to write a single byte to a file, you have to allocate a block, right? So at that time, you will allocate a block. How do you allocate a block? You go and find an empty block here, and you give it to the file. You say that it is given to the file. So assume an empty block is block 5. So assume this block is allocated to file. Okay, so file starts at block 5. Okay, you keep this information somewhere as part of the FCB or as part of the directory entry corresponding to the file. Okay, so now this is the file. So you can write some data into this block. Okay, so then if you filled up that block and would like to continue writing into the file, that means another block has to be allocated to file. So you go ahead and find another empty block. So assume now this block is empty. Okay, so you allocate now that block to the file. So this will be the next block of the file, right? So this is the block 0, block 1. Relative block number will be 0, 1, right? So you can go ahead and write into here, but you have to write here also put some information here, right? What? What's that? Next pointer, right? There you have to add information about the next block. What is that? The address of the next block. So you have to write here what? Which value? 3, right? So the address of the next block is 3. Okay, block number of the next block is 3. So you put that information into this block. Okay, so that when you go to this block, using that information, you can also reach to the next block. Okay, so assume you grow the file further, add some more information, you allocate another block. So let's say this is a free block. You allocate that to the file, that block to the file, and also you have to install a pointer here, so that it will point to the next block. So here we have to write what? 8, right? So that we have a pointer to the next block and so on. So assume you grow the file further, you allocate that block to the file, and you put a pointer here to point there. So block 8 will have a pointer now to point block 10. Assume this is the last block of the file, so you can put an invalid value here or a null pointer and so on, okay? So then these are the blocks allocated to a file. Relative block numbers are what? Block 0, block 1, block 2, block 3, okay? The absolute block numbers, the disk block numbers are what? Block 5 is allocated, block 3, block 8, block 10. These are the blocks that are allocated to a file, okay? So now let's discuss this allocation method. So it's a simple, right? So the information that has to be maintained in the directory entry or in the FCB, file control block for the file, is not that much. To reach out all the blocks of the file, we just need to keep the start address, start block number, okay? Which is 5 in this particular case. Once you have that, you can access all the blocks of the file. You can go ahead and read block 5, then go ahead and read block 3 and so on, okay? So external fragmentation problem is no longer exist because any block here, any free block can be allocated to a file. You will not have a block that is free and that cannot be allocated, okay? You will not waste a block. So we eliminate the external fragmentation problem, no waste of space. But the difficulty here is the random access. Random access will be very slow and costly. You can perform random access, but it will be costly. Why? Assume you would like to jump to that location in the file. What do you need to do? You cannot immediately say to me, without going to the disk and accessing some blocks, in which disk block that byte is stored, right? You should do what? You should go first to block 5, and then block 5, for example, you should, for example, compute how many blocks has to be skipped until you come to here, okay? So you have to compute that. After that, you have to go and visit that many blocks first to obtain the address of the block containing that byte, okay? So you have to go first to disk block 5, learn the address of the disk block 3, then go to disk block 8. If that byte is in disk block 8, then you can access it there, okay? So it is not easy to access an arbitrary location in the file. It is possible, but it is costly. It causes many disk accesses, all right? So therefore, random access will be quite slow if you are implementing linked allocation as it is, okay? We will discuss how we can make it efficient later on, but let's look to this computation now. Given an offset here, how can we obtain the corresponding disk block number and displacement? Logical to physical translation. So assume, or mapping algorithm. Assume we are given a logical address, an offset into the file. So we would like to find the corresponding disk block number and displacement inside that block, okay? So what do we do? So we first compute how many bytes are there, okay, to keep the data. So what is the data side inside the block? What is the maximum amount of data that I can store in a block? So what is that? It's basically the block size minus the pointer size, okay? Right? So if I divide the offset here to that number, the data size, what do I obtain? I obtain the relative block number where that offset is or corresponds, right? So if I divide the logical address or offset to the data size in a block, which is block size minus pointer size, if I divide that to this, then the result is the relative block number. The quotient, the integer division result, will give me the relative block number. And the remainder will give me the offset or displacement in the data. Okay? So then the block to be accessed will be, for example, if the result is Q, integer division result is Q, then the block to be accessed will be the Qth block, disk block, in the linked chain of the disk blocks representing the file. And displacement into the disk block will be R, remainder plus the pointer size, assuming the pointer is sitting in the beginning of the block. Okay? You'll understand that with a better example that we will do. Okay? So assume the block size is 1 kilobyte. Okay, 1024. This is the block size. Assume pointer size is just 4 bytes. So in a block, we have 4 bytes for the pointer. Block size is 1024. So the data size will be what? 1020, right? Bytes will be data. Assume we have a file that is 4000 bytes. Assume we have a file that can occupy 4000 bytes. Assume these are the blocks that are allocated to the file, okay? And the file starts at disk block 5. Assume this is the case, okay? So this is the block, first block allocated to file, next block, okay? So these are the relative block numbers, okay? 0, 1, 2, 3 are the relative block numbers. So we want to find out the disk location corresponding to file offset or logical address 2900. So I wonder where that offset is sitting on the disk, okay? If I want to access that portion of the file, that address in the file, to which disk block I should go and which byte in that block I should access, okay? So this is the question. So what we should do, what do you think? We should divide that offset to what? 1 or 24 or 20? 20, right? Yes, so we should divide that to 1 or 20 and the result is 2. That means 2 is what? Relative block number, right? So that means I have to follow the chain that many times. So the chain starts here, relative block number 0, right? Follow once and follow twice, 2 times, right? And go to the relative block number 2, which is corresponding to disk block 8, okay? So actually the corresponding physical block is block 8. So I have to access that disk block. But which byte inside that block? Which byte inside that block? What is the displacement into the block? This is the question. So I have to make a mod operation, right? So 2900 mod what? Mod 1020, which is 860. This is the displacement into the data portion of the block. If I am wondering about the displacement into the block itself, I have to add 4 to that, right? So 860 plus 4 will make 864. This is the displacement into that block. I have to retrieve that byte, okay? If I would like to retrieve, for example, that byte of the file, I have to then retrieve that byte of the disk, okay? Is it clear? The translation mapping, any questions here? So we can stop here and have a break and we will continue after that.